All right, let's start. So last time we talked about vulnerabilities. We talked about different kinds of software security, software vulnerabilities, but that's not complete. So today I'm going to talk about another type of vulnerability, and that is the so-called Stack Overflow. I believe that some of you have heard about that before. And I will talk about current existing defense for Stack Overflow. So today we're gonna the entire topic is gonna be about Stack Overflow. We're gonna talk about the attack and the carding defense. So also today is gonna be the last lecture for software security. And starting from the next lecture, Adam will be here talking about cybercrime. So before we start to talk about the actual technical stuff, let me first make an announcement about logistics. So there will be no class on Monday because we're going to rotate. And then starting from the next week, the live session will be on Tuesday and Thursday. So this also means that today is going to be the last live session for Monday and Wednesday students for you guys, throughout the entire semester. So for the rest of the semester, which we don't have too many courses left anyway, those live sessions will be on Tuesday and Thursday. I saw you guys are having a bad phase in the chat, and don't worry about that. I mean, there's always videos, and then you can just jump into the other section. Also, in terms of homework, the fifth assignment will be released probably in next week. I am working on that right now. So I'm hoping that I wrap it up so that you will be able to get it in early next week. And again, we will announce it in Piazza. You will see a web page talking about this entire assignment 5. So you can just track your Piazza announcement or track the course website. Once it's long, you will be able to start your assignment 5 very soon. All right. Do you have any more questions? Oh, is it our last assignment? I think so. Because after that, we're going to have our final CTF very soon. So I believe that will be the last assignment. I will double check with Adam, but I would say 80% likely that it will be our last assignment. And question, did I post the last assignment? I guess you mean this grade, right? Not yet. I will post it up when we finish grading. And then final exam is kind of assignment. It's yes and no. Final exam will be kind of midterm exam in a way of CTF. So you will have another CTF tackling those interesting challenges that covers through the entire semester, covers the content of the entire semester. All right. Take-home CTF? Yes. The final will be take-home CTF. Assignment 5, again, it will be announced the next week. Okay. All right. I'm gonna call it an end for logistics, but if you still have more questions, you can just send in chat or post in Piazza and we'll answer those questions there. And now let's start to talk about the actual technical stuff for Stack Overflow, since we will have a lot of a lot of stuff to talk about. All right. So last time we were a little bit in a rush in the end, so let me just recap what we talked about in last time. So last time we talked about how Stack works across functions. Although we didn't finish that, we just start with looking at how function starts. But today, actually, let me just start with how Stack works within the function first, in case that so that you won't feel lost. So let's first talk about how Stacks looks like when when one function is executing. Okay. If you have questions, type your questions in chat, because this will be very important for you. This will be very critical to your assignment. And it's very likely that you will have questions. If you haven't learned about those kind of stack layout from other courses before, so if you have questions, do let me know. And also I would like to know if those content has been covered in 230, since many of you have learned about MIPS before. So if this is also covered from 230 or other ASU courses, I also would like to know about that. So please type in chat so that I will be able to know those contexts. All right, so first let's start to talk about stack. I'll talk about how stack works within a function. Okay, so suppose that we have a function. I showed in the left, it's a function called check. You don't have to go through this function. You don't have to understand what's going. But what I want to show you is that inside the function check, there are two local variables, right? So one is called path, and the other is called res, right? It result res. Okay, for stack, when this function is executing, those local variant, local arguments inside the function will be stored in stack. So this is how stack works for a function when this function is running. So basically it stores those local variables. And if you look at the right-hand side, that is a stack. And the stack, the upper side is so this is low address. And this is high address. And you found that there are two variables. Those are the local variables, right? This is path, and this is res. Okay. So basically, this is how that works for stack. Stack stores local variables for you. And whenever you manipulate, whenever you operate on those local variables, you may change the value. And then accordingly, those values on the stack will be changed as well. Okay. And besides that, there's something more gonna stored in stack, which is these two guys. One is saved RBP, meaning that this is the register value of RBP for the other function. And I will talk about I'll talk about the other function later on. And another thing is saved RIP, which is a saved value for the RIP for the other function. And later on, we'll talk about the other function. All right. So this is how stack look like. And you may wonder that, what will happen if we have multiple functions? And that's very practical. It's very likely that you write a program and then your program is composed of many functions, right? So when there is many functions, and then doesn't mean that there are many stacks. The answer, I would say yes and no. Actually, there is only one stack space. So it's the entire program have a big stack. I'll just write here, stack. But then RSP and RBP, it controls the current stack. So you can consider that we always just call it a stack frame. You can consider this as a part of the stack that is in charge of a particular function. So if you look at check, then you only look at this part of stack. And then when the program is executing its running function check, then you look at this place. And then when this function returns, RSP and RBP will change to another value so that it will point to the other part of the stack that is, the function that the check returns to. All right, and I will talk about that later on. But right now, just keep in mind that RSP, RBP are two registers that kind of scope the stack for a function. And once this function returns, this stack disappears, all right? But then if the function is called again, then this stack will be created again. And I will talk about that now. And you will be able to understand more details about that when we talk about how stack works across functions. So far, so good? Cool. Okay, so let's start. Suppose that we have two functions now, all right? So we have function bar and we have function full. And I suppose that right now, what I'm showing here is the RSP or RBP, like the stack frame for function bar. All right. So if you look at the stack, you have low address, high address, and then you have RSP and RBP, which kind of scope, which is scoping the range of stack that you cared about for function bar. And now we're gonna call function full. Okay, and then for function full, before function full is executed, the first thing it's gonna do is that it will save the current RIP, like which is the instruction of printf, save that value onto the stack. This is called saved RIP or the so-called return address. So this tells the computer, or this record the next instruction to be executed if function full returns, okay? And then next, we start to execute those instructions in full. And this is the instruction in full. And you see that the first instruction, it says push RBP, all right? So when it push RBP, it means that it pushed the current value of RBP onto the stack. And this corresponds to the change of this stack item. So you have one more item storing on the stack, and this is the current value of RBP. We also just call it saved RBP, okay? And then the next instruction says move RBP RSP. And keep in mind that this is Intel syntax, if you still remember. So it's gonna be on this direction, right? So you move the current RSP value, you copy that value to RBP. And this is why you found that, currently RBP's value is equal to RSP. So both registers point to this location, which is the bottom of the stack. It's like the lowest address of the stack. All right. Okay. Then the third instruction, what it does is that it subtracts RSP by a certain number, like a number that may change for different functions, but it's like, a number, an absolute number. And in that way, RSP no longer points to, sorry, 1 second. RSP no longer points to this location, right? And then instead, RSP starts to point a new location. And in this way, if you compare this with the original bars, RBP and RSP, if you still remember, this is where the original RSP. Give me a second. There's something wrong with my iPad 10 pencil. Okay, here we go. This is the bars RBP. So By the time a bar calls full, we move RBP up, and then we move RSP also up, so that we establish a new frame for function full. So this area is for function full. Between these two areas, there are two items saved over there, right? This one and this one. One is saved RBP, which is the value for bars, and the other is the saved RIP, which is the value that function full will return to. Okay. All right, so far, any questions? Good. Good. Okay. All right, and now let's talk about how function returns. Okay, so far it is how function full it starts to execute. And now let's suppose that there are a bunch of actual operation in the middle, and now is the time for us to return, or say to leave function full. So that's the time that function full is finishing, and we need to go back to bar. All right, and let me clear this out. I can't clear it. I need to force clear it. Hold on. Cool. Okay. So now let's talk about function returns. So for function returns, usually there are two instructions going to be used consecutively. All right. The first one is called leave, and leave instruction is equivalent to two instructions. One is move RSP RBP, and the other is pop. All right. So let's look at the first instruction, move RSP RBP, what it does. And then keep in mind that, again, this is Intel. So when we do move RBP RSP means that you copy the value of RBP to RSP. So if you remember, originally here is RSP, but then after we copy the value from RBP to RSP's value was recovered to this place. Okay. And then next, we're gonna pop RBP. So when we do pop, this value will be popped up, and this value will copy it to RBP. And also, because this is stack and RSP always points to the bottom of the stack, RSP will also go lower. So it will be like this, right? So in this case, then RBP have this value, and this value makes it points to the original place, the original base of bars stack. And then RSP also was like it's actually added by 8, meaning that the stack got popped up one value, so that currently the bottom of the stack is at this location. Okay, and then the next is return. So what return does is also kind of like 2 steps, or say you can also just consider that as one instruction, which is you pop RIP. So you pop the value from the stack, and then you put that value onto RIP. And keep in mind that RIP is the register that always points to the instructions to be executed. All right. So in that way, we recover the instruction value so that the computer will know what is the next instruction to be executed. So in this way, we successfully go back to function bar, and you see that RSP, RBP also, the value of them got restored, and RSP points to the next instruction of function full. And this completes the entire process of calling full and a return from full. All right, so this is how stack works for functions, especially when we call a function and return from a function. And then now let's come back to the stack. And why do I want to talk about that? Because I want to introduce this Stack Overflow vulnerability. And that vulnerability take advantage of specifically this property that is designed as the stack, which is that the saved RIP, which is the saved return address, will be actually stored on the stack. And then on the high level, the goal of Stack Overflow is to overwrite this value to be something that is more interesting. It can point to an arbitrary place that will start to execute malicious code, or some code that is not expected. That's not expected as the same as this saved RIP. So how to do that? So one way is to use overflow, especially overflow on a stack, in a way that we find a local variable, and then we try to write this local variable. So we start to write the local variable, and then not only just write, but also overflows the local variable. So we will overwrite the entire chunk. And two, we overwrite the saved RIP address, and then we will have that point to somewhere that we're interested in. All right, so this is the high level idea of Stack Overflow. And again, what it tries to do is that it will overwrite local variable, overflow local variable, so that it will overwrite the return address, and then let the overwritten return address point to somewhere that is malicious. Okay, good. And then next, let's take a look at this example. So let's take a look at the left-hand side code, function check. I'm going to give you a couple of minutes and let you to understand what does this function do. And please type in chat. Let me know what you think about this function. What does this function do? Sam has said that this program, given an ID, it checks for something in the file. Yes. And Andrew said it's checking, looking for if given a mismatching to the valid path that was input. Yes, so it's like this is the check function that we had previously when we talk about path traversal. So consider valid path to be like check this path doesn't have specific special characters, such as dots, those kind of special characters which will alter the directory. Okay, and then combining Sam's answer with Andrew's for this function, what it tries to do is that, it takes ID as an input, right? And then it copy this value, ID, the value of ID to stream path. And then it will check if the path is valid. So basically it will check if this path is a true path. And then after that, when I say true path, it means that this path doesn't contain special characters which will make the the following cat or the following file read beyond the directory that is supposed to. All right. So after valid path, it then use execl to call the command cat. So it's like read the file following this path, and then return whether or not this read operation is legitimate. So if it's legitimate, then it will print check pass. Otherwise, it will return check failed. All right. Okay. So this is the high level, like the semantics of the function. And now let's talk about the vulnerability. So the vulnerability is that if someone give a string like this ID, which is longer than 15 and even longer than this. For example, I can give, ID A, and then many, many, many A's. Okay, let's say I put here 50 characters. All right, so what will happen if I put 50 characters? So the path, this argument, will then become records A, many A's, right? And then for valid path, it only check like if this path is kind of legitimate, and it looks legitimate. You don't go beyond the record. It still enter the folder, right? So it looks fine. And then it will just call on cat and see if this file exists, or if it exists, then it's try to get the content from the file, and then we'll print whether pass or failed. All right, and then the problem here is when we run this statement, when this statement is executed, path only occupies, like path, this variable has only 50 characters, which is 50 bytes. So if you look at the stack, if here is path, then this is only 50 bytes. But if we give ID for 50 characters, then this will be more than 50 bytes, right? So path will be stored by more than 50 bytes, and it will then start to overwrite the next items here. And if we make this ID even longer, so it's not 50, let's say 100, okay? If we change it to 100, then you will see things like records, right? And then A, many A's. Here is also A. And even the saved RIP will become A, because it was overwritten by the time that we execute as printf. There's no check to see after doing as printf if the final string is beyond the boundary of path, which is 50 characters. So there's no such check, which comes to this issue that something, on the stack will be overwritten, and even worse, the saved return address will be overwritten. And then if that is the case, then by the time that check returns, the stack or the computer will consider this place stores the saved RIP. It will try to start from there to execute the rest of the instruction. And we can change that to some value. We can just like users can provide whatever value. It can be something like AAA. It can be like that beef. It can be, or a function. It can be like a function address if that function does something that is, in our malicious intention. So in that way, you can change the value of ID, feed this ID as the input to the program, and then make this ID longer enough so that it will overwrite the return address by the time that check was called, and then it will go to a malicious function. All right. Okay. So that's pretty much about buffer overflow. This is a high level idea. Although for buffer overflow, there's still like more advanced ways to like execute the code or go to somewhere else. But I think for now, let's just stop right here and then let's do a practice together. So I hope that you still have the account for your midterm exam. And if so, you can go to your midterm exam website, which is ctf.csc365.io. Note that it has HTTPS, all right? So you need to make sure that you type HTTPS, not HTTP. Go there, log in your account, and then you will see a challenge called Baby Stack. And let's play with that challenge together. Okay, so I will give everyone 2 minutes to log into the midterm CTF platform. You should be able to see a new category called software security and a new challenge called Baby Stack. Let me know if you managed to get to this page. And we're gonna work on this together. Or if you want to work on this by yourself, also feel free to do it. Cool. Yep. Thanks, Jose, Justin, and Samuel. Good job. You guys are on the page, and Samuel even already SSH'd in. That's great. If you forget your password, you probably have to reset it. All right. So now let's take a look. And by the way, will be the way that you like for your assignment. And probably in final CTF, you will have something like this as well. So I guess this is also going to be a nice chance for you to kind of get familiar with the environment, or like the environment plus a software security challenge. All right. So it's like, this is Baby Stack. You already see that. And then click that, you'll be able to run the challenge, right? And then it will tell you that you can connect with this command with your private key. I hope that you still be able to find your private key. Otherwise, you can just change your settings and then replace your public key with a new generated key. All right. Okay. So now let me check. Okay, this is Tiffany's account. And we can start with playing around in the terminal. All right, so you see that you have a challenge here. It's called software security _ baby stack. And then you can run this. So it says that we will now read in some bytes. So you need to give it some bytes. And also it tells you that in this challenge, you need to find and jump to a win function. Basically, there's a function with the name of win. And this win function will read in a flag and print it. So all you need to do is to figure out where the win function is, and then figure out a way that to make this program to execute the win function. And then you'll be able to get a flag. And now we can type in some bytes and play with this challenge and just like put some random bytes. Okay. And nothing else pops up. After putting some bytes, it just finished. All right. And now time for us to understand what this binary does. Due to the limit of time, I'm not going to reverse engineering this challenge. And you also don't have to do it for now. So if you go to challenges, enter the folder, you will see software security folder, and then you will see babystack.c. Okay. And there you will be able to see the program. This is the source code of the program, although this was is a little bit different. But before we talk about here, let's just quickly go over this program. Actually, this screen is a little bit sketchy. Let me download the source code. And also, actually, let me just SSH to the terminal, to the container, and then we're gonna read the code together. Okay, so file path about the source code is under challenges/software security. And then also you should have the same name as well. So basically it's challenge and /software security /baby stack.c. All right, now I am going to log into, let me share my screen again. So SSH using my key. I think it is ctf.csc.io, right? Okay. Okay, now I am in. Oh, not this one, sorry. Give me a second. Now I'm a little bit confused. I need to log into the, oh, it's CTF, sorry. ctf.csc, oh, here we go. Okay, so now we are in this session. And let's look at the source code. Again, let's start with main. Let's take a look at the main function. There's some assertion, and then we see there's a bunch of printf. It just like print those information. It's same as those information that you see from the session, right? Okay, and then after that, there is a buffer with a scope, like with some length. It's a buffer with hex 330 characters. And then it tries to read from input and then stores that in the buffer. And then, however, if you found this, you realize that the buffer is only with the length of 330, but we are reading more than 330. We're reading hex 430 bytes, which is much more than the length of the variable buffer. And by the way, guys, if you look at your code, you will find that this is different. You will have another value. And this is just because the way that we generate the challenges, everyone will get a different offset, different values for the buffer length, and that is randomized. So you'll see a different value. But overall, the structure of the source code is the same. So you have a buffer, and then this program takes standard inputs, and then will store that in the buffer. And you see that this buffer, like what you can provide, the inputs to the program will be longer than the length of buffer. And that gives us a chance to overflow the buffer and overwrite the return address. Okay. All right. So now let's start to, try to write this code. So first of all, let me just try to put some random strings. You know that you want to be very long because you want to overflow the buffer, right? So let me just take this input and then write a very, very long string and see what will happen. So what I'm going to do is I'm going to read a very, very long string and then store it in a file. And then I'm going to redirect that file as a standard input and then execute the program with that standard input. Okay. So then I am going to use Python Python.c means that you just write your code here and it will execute it. So do a times. Okay. All right. So this is the way that you can write a Python code very, very quickly, and then I'll just output. And you want to store it to somewhere. So you can't store it right here in the root directory, but you can store it in your temporary file, like in the temp directory. We just call it AA because there's so many A's. Okay. And then if I do software security, this like this program, and then it takes this as standard in. All right. So you see that the program executes, and then it has a segmentation fault. Let me do this again because I just happened to click something. Here we go. Okay, so there is a segmentation fault. All right. Okay, and now what we're going to do next is that we are going to look into the disassembly and really figure out how to overwrite, how to overflow the variable such that we can overwrite the return address. Like we want to locate the return address precisely so that we know where we're going to overwrite to. Okay, and then question, what's the command to save the Python line to AA? It's I use this Python C, but you can just use other ways. Okay, so now next what you could do is, I mean, there are many ways. You can do this in a static way or you can do this in a dynamic way. Actually, let me just start with a static way. Ops dump, okay, -d, software security. So this means that you want to take a look at this assembly, and we talked about that in previously, like in the previous reverse engineering class. Okay, and then we go to the main function. We know that the vulnerability exists in the main function. We know that the vulnerability exists around the place that it starts to take inputs, right? So and we know that's almost like in the end of the function. So I just ignore what has happened before. Find that, oh, here is the place that I start to read, right? So if your student remember the source code, it tries to read, and that is where, like, this is around the area that the vulnerability happens. Okay, so here we are. And let's just remember this address. Okay, I'm gonna put it on the left-hand side, just using this temporarily as a notebook. So it's 4014EE. That is the place that it's around the the point of interest, around the vulnerability. All right, so now let's try to run the program. So I'm going to use GDB. Yeah, just run it. And by the way, this one, I mean, in this current in the CTFD, in this environment, we don't install fancier debugging tools. So, and in fact, I would recommend you to download this file to your local machine so that you'll have, your nice environment to debug it. Otherwise, you have to suffer from this like plain vanilla GDB, which, I mean, it's acceptable because but I don't think that it's acceptable for everyone. For me, I'm okay with that because I was in the age before Pondabag, those kind of fancy plugin was invented. So I already get used to using an old version, the plain version of GDB. But for you guys, if you already use Pondabag or like Jeff, the other plugins already, you may not be able to get ready to this vanilla version. And feel free to download the binary and then run that in the actual Linux system, like your local Linux system. Okay, so now I'm just use this, and I'm gonna set a breakpoint, this place, right? as I said, this is a place that is interesting. So let's do this. 4014 EE. Okay. We start to run, but we want to run this with the input that we just generated. Now we set a breakpoint. We stops here. And then let's take a look at, so I was told that the bottom of my screen is getting cut off. But I can see the bottom of the screen, from the other client, Zoom client. Let me know if you still have this problem. Okay, thanks, yeah. Matthew, you probably want to fix it on your side. And let me just continue. So here we're at this place. We know that we're about to execute something. We're about to execute the read function, right? And now let's see what's happening around the read function. And in the meanwhile, I don't need this as more because I already put this aside. And then I will use this as the way to eyeball the disassembly of the code. obj dump -de. Okay, so still the main function. Let's go down. My terminal got stuck. Very nice. Here we go. Okay, so this is the place, right? So this is the address that we're interested in. So now we have the static and the dynamic. Okay, and let's take a look at the static on the left-hand side. Although also like you can take look at this assembly on that side if you use this command, x like 20i, and then followed by the address, like some address around here. And this means that you want to inspect the memory for starting from this address, and I means that you want to inspect the memory in the format, in the type of instruction. And let me just put 5 instructions, so you also be able to see what is happening around here. But like in the left-hand side, the static view will give you a nice view, more complete view about the disassembly. So you can have another window just for you to look at the disassembly. Okay, so now we see that this is read. And if you still remember when we talk about reverse engineering, we talk about calling convention, right? And then we talk about for x86, 68, according to calling convention, register, I'm going to ask you guys, which register is for the first argument? And which register is for the second argument? Do you still remember that? If so, type in the chat. If not, just Google it and you will get it. All right, yep. So the first argument will be in register RDI. And then the second argument will go to RSI. And then the third will go to RDX, right? And then if you look at this read, now you know that, okay, the first argument is RDI, and in this case, it's the result, the value is 0. And then the second argument goes to RSI, and again, the value will be equal to RAX. But what's the value of RAX, right? And then let's just go up, find the place that RX got assigned a value, which is this place. It is LEA, means that load effective address. And to be simpler, it just means that RX is equal to RBP minus hex 50. And you may wonder why you want to use LEA instead of subtraction. And the answer is that LEA turns out to be more efficient than subtraction, just like circuit wise. For computer, LEA instruction runs more quickly than sub, so that's why they use this. Anyway, not important, but now as long as you know the meaning, you're good to go. So here you know that RAX is equal to RBP minus hex 50. All right. So, and also you know that since we are executing here, and we know that for read, if you remember, the first argument is like the file descriptor to read. And then the second argument is the actual buffer, like the address, or say the address of the characters strings that you're going to read to. So let's take a look at the value of RSI, the current value of RSI. So I type this. P means that you want to print the value, and X means that you want to print this in a hex way, like in the hexadecimal. And then RSI means that the register. This is the value of the current RSI's value. So you're gonna, once this read function is called, the string will be like the string that you give the program will be stored at this particular location. Okay, and now let's take a look at like how far does this location is away from the saved pointer, because the goal for us is to override, to change the stack that stores the saved pointer. So you could do info frame. Using info frame, you will get some values. So, and frame here is the so-called stack frame that we repeatedly talk about in today's class. So that's a stack frame. And then for saved registers, it shows that the saved RIP is at this particular location. And then we know that RSI, which will be the input that we're going to give, is at this location. So how far away between these two? Can someone just calculate and let me know how many bytes are away from this location to this location? Great. Yes, so it is hex 53. All right. So now we have a perfect go. We know that the string will be stored at this place, right? And then we need to overwrite the saved RIP so that we will get to the function that we're interested in, which in this case is win function. All right. So next, actually, let me just do one more instruction, and this will help you understand this a little bit more. So first of all, actually, let me take a look at this address. You can use X, and also you can specify like, how long you want to look at. So I'm writing, this is okay. This is slightly better. This is just like different way for you to specify the format. So you want to know that, okay, this is going to be the start of the string. And right now it has this value, right? And let me just execute one more instruction. Actually, let me set another breakpoint, because next instruction goes into the read, and I don't want that to happen. So it is 1 for F3, continue. All right, and now let's take a look at this place again. So it's all over AAA, those inputs that we give to the program. And now let's look at info frame again. So you see that here is still the same place that stores the original RIP, but save the RIP, the value got changed. It changed to AAA, right? Which is the input that we give them. This is nice. So this means that we can change it to any value that we like. And now the question is, what value that we like, and then how we're gonna know that, like, in order to overwrite this particular location, how we're gonna change our input, like to this particular, like to the bytes inside our string so that those bytes will overwrite this place. And as Matthew said, the offset between the start of the buffer to the actual location that saves the original, the saved RAP is hex 53. Then what we need to do is that we want to craft a string. It will be like A, many A's, right? And then this is 53, hex 53 bytes, right? And then followed by that, we need to then put the address of wing. Then we'll be able to override the saved RAP. Okay, and then question why it is hex 53. Hex 53 comes from here. Actually, is that really hex 53? No, actually, it's hex 88. Sorry, it's 88, so it's not hex 53. Right, hex 58 it is. So let me change this. It's not 53. It's hex 58. And again, the way that you get it is to have this address, right? And also you get the address of the buffer, and then you subtract them together. So you want to subtract this address by this address. Okay. And thanks for asking this question, Samihan, and then thanks for correction, Matthew. Now we are good to go. All right, so let me just exit this. Actually, let me not quit it. I'm gonna open another terminal, and then we use another terminal to write the attack, and then use this terminal to kind of replay the attack, and then inspect the memory. All right, so let me do SSH. Okay, so we're here now, and then we're gonna write this, and then let me just put something here. Okay, I'm gonna write a Python code, and that code is very easy because first of all, I want to just put buffer is equal to something not important, but it has to occupy it for 58 hex 58 positions, right? And then plus the function, the address of wing, and then we need to figure out where the wing is, and we can use the left-hand side static view. We can find function wing, the address of function wing. Okay, so here we go. It is hex 40112 FD, right? So now it's the time for us to come back to little endian, and then talk went back to how we're going to convert and value to little endianness. So we're going to use struct.pack and convert that to little endianness. And then it's a long, which means that this is 8 bytes because we're coping with x86 64. Okay. And then put this here. This is the address of wing. Okay. Good. And by the way, because this is Python 3, we need to be a little bit more careful because struct.pack and will return a bytes. Okay. And then we just open a file, attack, and write that buffer in, and we are good to go. Let's try this. Yes, that's correct because I didn't import it. Cool. And then let's take a look at attack. Looks okay. And then look at the, actually, let me use Hackstomp since we already know that. It looks cool. So we have hacks 58, right? So this is 1, 2, 3, 4, 5, 6, 7, 8. Hacks 58 bytes of 41A. And followed by that will be the address of Wing. And then we encode it in little endianness. So that's why we have, 8 bytes for that. All right. Now let's try to run this. So if I am going to run this, then software, and then temp attack. Okay, so now we got a flag. And before we move on to the next part, I want to try this with the breakpoint so that you will be able to see the change in the memory. Okay, let me clear this out. And then let's take a look at here, the right top panel. So we run, and then we run to take attack as the input. Cool. Start. Okay, now we're gonna start to read bytes, right? And then if you still remember, this is the point that we start to read, right? And then the current RSI represents the buffer that we're gonna read into. So let's do RSI. Take a look at the value over here. So it's like something pretty messy. Let's do even more. It's pretty messy, right? And then info frame, we see that the saved RIP is at this location, and the current saved RIP's value is this value. Good. Okay, and then next, we're gonna continue. And then let's take a look at the location buffer again. This is all A's, right? And then here it changes to the value of a Wing function. And in fact, if you look at frame, we found that saved RIP becomes the address of Wing function, right? And that is the way that we will be able to get the Wing function. And then if you continue to execute, it'll tell you that you win and here's your flag. All right. And now we got a flag, and then you can just submit it. Challenges. And check if that is correct. And yes, that is correct. And you may realize that even though you're correct, there's no green here. That is okay because of midterm, we just froze. We phrase the website, but as long as you see correct, then you're good to go. Okay, so I saw a bunch of questions. Can you show the babystack.c file again? I mean, if you have it on your site, if you can log in, then you will be able to see babystack on your site too. But let me show babystack. And then meanwhile, answer the other questions. Okay, and then next question. Is this a practice exercise or spring it? This is a practice exercise. And then assignment will be similar to this. And then Michael says that all you need to do is to vim.c file to get what your buffer sizes are. Not quietly, at least in the current setup. It's just like the source code that we're showing, like this buffer size, is different from the buffer size that we just like we just used for the binary, right? So it's like here it has hex 330, but for our question, for our task, which I just did, the binary, it has hex 50. Okay, and then more questions. Can you show, okay, I have already showed the source code. Do we have to submit our flag? I mean, you have to do that for assignment, but now you don't have to do it. And if you still don't quite get this, I encourage you to go to my office hour or watch the video again, because we're running out of time right now. I can't explain too much details, but I will be very happy to take any of those questions that you have from Piazza or from, or during office hour. Okay, and you want to see the buffer one, the source code that I write for the attack, right? Here we go. All right. So guys, this is pretty much for our attack. And then next, I am going to talk about defense. I'm gonna show this for a little longer file, like a longer while. Actually, let me just copy paste that in our chat so that you will be able to see that. Yes, I very much encourage you to rewatch this recording step by step. And I very much encourage you to, do this, do this analysis, write this code as the, what this recording tells you, do that step by step. Like you pause your video, you write this, and then you pause the video, you continue it, and then you write the rest. Question, where did I get this address? I disassemble the program using opstomp, and then I get the win functions address. All right. Let me reshare my window. And now let's continue to talk about defense. So first of all, recap, what do we do for exploit? So we overflow the buffer, right? And then we overwrite to save the return address. And then for the third and fourth, we don't talk about shellcodes here, but like we just overwrite the return address and then change that value to some value that were interesting, or to those instructions that were interesting, such as the win function. So let me just cross this out so that it won't distract you. All right. I mean, that is another thing, but we are not going to talk about that in our course. So the question is, can we stop the exploitation in any of those above steps? Okay, so the first defense means is the so-called stack canary. All right, so what it tries to do is that between the local arguments, right? For example, the path argument that we have, right? So between the local arguments and the saved RBP and RAP, we insert something that we call it canary. And then we're going to check the value of canary by the end, like by the end of the function. And also before that, like when the function starts here, we insert a random value on the stack. And later on, by the time that we're about to leave the function, we check this value again. And if an overflow happens, that means that stack canary's value will be overwrite, right? Because this is a random value that it's going to be very hard for people to guess out. So if you put A, many A's here, and to the save the RAP overwrite the value, then you will also overwrite the value at stack canary. And in this way, you will be able to detect that. And this has been nicely implemented in both Linux and Windows. This is the so-called stack canary. All right. So as I said, you will also overwrite canary, and stack canary will be able to detect that. And usually the canary value is a random value. It's a 8 bytes for x6, 64. And it is predefined per thread before main is actually called. So you can get this information if you like run the program, but then usually when you have to debug in order to get this information. Every time it's changing. It's a random bytes. Okay, I'm gonna skip this and then talk about bypass. So it sounds like stack canary is powerful, right? Because whenever you overwrite it, you will be able, stack canary, you have to touch it. You have to change the value. However, there are many ways for you to bypass that. For example, you can kind of leak the canary value. If the program itself has an arbitrary read, so it's like, you can specify a memory and then let the program output the value inside that memory. Then you can locate stack canary, get that value, and then by the time you overwrite the canary, you just overwrite it with the original same value. So in this way, even though you overwrite it, the value doesn't change. And there's no way for stack canary to detect the difference because there's no difference. Okay. All right. And then you can also just, like, as I say, you can leak this canary value, and then you can print it out. You can get the value. And then you can just even overwrite the predefined canary, because usually those predefined canary, it's in the higher address of the stack. And if you really just overwrite a lot of them across functions, you not just overwrite one function's frame, you overwrite the next function frame again and again until you reach the actual predefined canary. You can also change that value and making sure that that value is the same as the stack canary in your current function frame. Okay. Then next is that, when we overwrite the save the return address, then we need to think about what address that we want to overwrite, right? So it's like in this case, we need to figure out the address of win function. And we may need to figure out other things. We didn't talk about shellcode in our class, but like the shellcode is something that is on the stack, and then you can let the program to execute the content on the stack. However, for those address, there is a defense that can kind of like randomize those address, so that every time you execute the program, the address of the function or the address of the shellcode, like just the address of the places that you want to execute, is going to change every time you run it. So there's no way for you to know what exactly the value is unless you have some specific way to bypass it. This is about, so ASLR is short for address space layout randomization. And then, this is a shellcode thing. We're not going to talk about that. But like for us, when we have a win function, you may realize that the win function, like the address of a win function, got changed every time that you run it. And in that case, then there's no way for you to use it, no way for you to really call the win function using ASLR. When ASLR is enabled. Okay, and then there is also some ways for you to bypass ASLR. For example, you could, instead of saying, like specifying where it is, you use relative address, such as like jump, RSP, it's an indirect jump. I'm not gonna go look into the details. Okay, and then the other thing is XOR X. So W XOR X, it is another way for you to stop running something that is controllable by user's input. So again, like we only talk about the win function, but then there is also one way for us to execute something malicious, which is to use shellcode. And then shellcode can be stored in a stack. Basically, we're going to execute something on the stack. But then if we enable W XOR R, meaning that you could you can only do one thing between write or execute. That means that you can either just write or execute. If there's a place that you can write, then there's no way for you to execute that particular place. And similarly, if you can execute a particular location, such as win function, there's no way for you to change or to edit that function while your function is running. So if that is also enabled, then there's no way for you to execute a shellcode or something that is saved in the buffer, saved in a place that you can write. All right, so those are possible means to kind of like thwart us from doing Stack Overflow. However, there's still a way for us to do Stack Overflow. We're not going to talk about that in this course, unfortunately, but feel free to watch the videos that I posted on the channel. Those are like those Stack Overflow videos about, there are videos about ROP, about more interesting and fancier attack technique that will be able to bypass those kind of different defense means. All right, and that's pretty much for today. I saw some questions here. So will the CTF server stay active for us to go back and work this problem after lecture? Yes, I'm gonna keep this open. So you will be able to play with the server for a couple of days. I will probably shut it off on Friday because I need to set up a new server that will contain our future assignments. Is the next assignment our last one? Yes, it will be our last one. I mean, 80% of it. I need to talk with Adam, but it's very likely that it will be the last one. When will last class, what do you mean by last class recording? If you're talking about today's class, then I will post it tonight or tomorrow morning. Oh, if you're talking about the previous class, I think it's already posted. I mean, I uploaded to YouTube this afternoon. It may take some time to process, but I think it should be available. All right, let me stop recording.